Hey everyone, and welcome to The Explainer. I am so incredibly thrilled you're here today because we are tackling one of the most fascinating and honestly urgent challenges in technology right now. We're talking about how we actually teach artificial intelligence to know things rather than just taking a wild guess. We're going to explore the evolution of AI truth, tracking the leap from basic retrieval systems to incredibly advanced hybrid architectures, and we'll look at why this has suddenly become a literal matter of national security. Okay, we've got a lot to cover, so let's dive right in.
So, you know the feeling, right? You ask an AI a complex question, and it spits back this beautifully written, highly confident, and just entirely incorrect answer. We call this an AI hallucination. To understand why this happens, you have to realize that asking a standard large language model a question is essentially forcing it to take a closed book exam. It only has its parametric memory. That's the fixed information literally baked into its neural network during training. If its training data doesn't adequately cover your specific topic, or if the info is outdated, the AI doesn't usually just raise its hand and say, "Hey, I don't know." Instead, it tries to predict what a correct answer would look like. It guesses. And honestly, that is exactly what we need to fix. Enter our ultimate solution, Retrieval-Augmented Generation, or RAG for short. If standard AI is a closed book exam, RAG is basically handing the AI an open book. This is a massive paradigm shift for us. We are augmenting the AI's generation capabilities by giving it access to an external, non-parametric memory. Before the AI even attempts to answer your question, it actively searches a trusted, completely up-to-date library of external information, reads the relevant documents, and then uses that verified information to construct its answer. It explicitly grounds the generation in reality. And to see how we build this open book system from scratch, let's look at the mechanics of the traditional pipeline. Section 1. The Vector RAG Pipeline. How AI reads the library. A standard RAG pipeline is actually beautifully structured into four main stages. First is chunking. We obviously can't feed an entire corporate library into an AI all at once, so we break large documents down into smaller, self-contained pieces, like paragraphs. Second is embedding. This is where the magic really happens. We use a transformer model to turn these text chunks into high-dimensional vector representations. We're essentially turning words into complex math that captures their exact semantic meaning. Third is retrieval. When you ask a question, we turn your question into math too and search for the absolute closest semantic matches in our vector database. And finally, generation. The AI takes your original question plus the matched text chunks it just retrieved and synthesizes a highly accurate response. Take a look at the flow here. Up on the top, you see the offline indexing process, documents getting chunked, embedded, and stored securely in a vector store. Then, on the bottom left, the user enters a query. That query hits the embedding model, goes straight into the vector store to fetch the relevant contexts, and then, and this is absolutely crucial, both the query and the retrieved contexts are combined into a prompt that grounds the large language model's final response. It's this seamless loop of retrieval and generation. But, as you might expect with any new tech, there is a catch. Which brings us to Section 2, the plot twist, when standard RAG fails. When you feed a traditional vector RAG system something like a highly complex financial earnings report in a PDF, the traditional text chunking completely loses its mind. Actually, scratch that. It doesn't lose its mind, it's just blind. It completely fails to see complex charts, graphs, and visual layouts because it's just stripping raw text. This is exactly where the industry is moving toward Vision RAG. By using visual document retrieval pipelines with models like Call-Pally and late interaction scoring, we build a system that actually sees the document as an image rather than parsing raw text. It effortlessly handles those visually rich enterprise documents. But what about pure text relationships? Well, researchers created an alternative called Graph RAG. Graph RAG views documents as a literal web of relationships, extracting entities and turning them into structured knowledge graphs. This is fantastic for mapping out connections, but Graph RAG has its own massive weakness. It generally underperforms when you ask abstract questions where entities aren't explicitly mentioned. So viewing documents purely as a web solves some problems, sure, but it creates entirely new ones. So what is the silver bullet? You combine them into something called hybrid RAG. Notice how a hybrid RAG approach brilliantly processes the exact same document in two entirely different ways. On the left, we see the vector RAG approach, breaking PDFs into chunks and converting them into embeddings. On the right, we see the graph RNG approach, using an LLM to process those exact same reports to extract knowledge in the form of triplets: subject, predicate, object, to build a robust knowledge graph. At query time, hybrid RAG fetches the broad, similarity-based text from the vector database and the highly structured, relationship-rich data from the knowledge graph. It gives the AI the absolute maximum amount of context possible.
Moving on to Section 3, Measuring Success and Failure, Engineering Realities. Recent software engineering research highlights several critical failure points when you're actually out there building these RAG systems. You have to optimize chunk sizes, which is incredibly difficult in text RAG because randomly breaking a paragraph destroys context. Vision RAG bypasses this by evaluating the visual page, but if your text chunks are too big, you introduce semantic noise and irrelevant tokens. You also still face hallucinations if the AI goes rogue and decides to just ignore the retrieved context altogether. Plus, as we discussed, traditional systems miss hierarchical understanding. The absolute crucial point from all this research is this: you cannot fully validate a RAG system on a whiteboard. The true robustness of these systems evolves during live operation, not just in the initial design phase. Now, this diagram outlines how we actually measure success and failure in the wild. We look at three critical pairwise relationships. First, how relevant are the retrieved documents to the original query? Second, how relevant is the final response to the user's query? And third, and honestly perhaps the most important, faithfulness. This asks, is the final response strictly 100% grounded in the retrieved documents? If the AI generates plausible statements that aren't actually supported by the documents we just handed it, that's a failure, no exceptions.
Let's look at how the different systems actually perform on these metrics. This data is from a fascinating study applying these architectures to complex financial transcripts. Vector RAG has perfect context recall, hitting a solid 1.0, but lower faithfulness at 0.94. Graph RAG improves faithfulness to 0.96, but its context recall drops significantly to 0.85 because it struggles with those abstract questions we mentioned. But look at hybrid RAG on the far right. It is unequivocally the superior, balanced approach. It matches the high 0.96 faithfulness of Graph RAG, it achieves the highest answer relevancy at 0.96, and it retains the perfect 1.0 context recall of Vector RAG. Whenever Vector RAG fails to fetch the right context, the system effortlessly falls back to the knowledge graph, and vice versa. It's an incredibly elegant solution. And as these hybrid RAG pipelines prove their dominance, they are rapidly scaling up to handle incredibly sensitive enterprise data, everything from private medical records to proprietary financial data. Which brings us to our macro view. Securing these AI pipelines is literally no longer just an IT problem.
Section 4, Security and Enterprise AI, Safeguarding the Systems. To highlight just how critical this has become on a global scale, we can look at the June 2026 White House Executive Order 1449. This directive explicitly mandates the prioritization of cyber defense for national security systems. It also officially establishes an AI cybersecurity clearinghouse to coordinate the discovery and remediation of software vulnerabilities. The order clearly recognizes that advanced AI systems are now critical infrastructure, and defending them requires highly coordinated action across both the government and the private sector. Furthermore, the policy outlines a really specific mechanism to safeguard the most powerful systems, defining a brand new category known as covered frontier models. For AI developers building these cutting-edge models, the government designed a voluntary framework. It allows developers to provide the government with access to these models for up to 30 days before they are released to the public. This gives trusted partners the time to test for vulnerabilities, protect against insider risks, and ensure the models absolutely cannot be weaponized by criminal actors to unlawfully access external data. It's a massive, unprecedented step in establishing structured security protocols for AI. Which leaves us with a final, rather profound question to consider as we wrap up this explainer. We've spent our time today exploring how to anchor AI to factual documents to stop it from hallucinating. But as RAG pipelines scale to query billions or even trillions of documents across the globe, we are effectively shifting the entire burden of truth from the AI's internal memory to the external databases it reads. So moving forward, who exactly decides which retrieved facts we trust? The immense power in the future of AI won't just belong to whoever builds the smartest model, but whoever curates and controls the libraries those models are allowed to read. Thank you so much for exploring this with me today.